Started. Okay, so we're going to start with the labs next week from next Monday, that is September 15th. Please take a look at your schedule and whichever day you are assigned to do the labs, please make sure that you know your lab schedule and everything. Your TAs will post their office hours, so most likely that's going to happen over this week. I'll try to work with them and try to make sure that they post their office hours earlier in this week so that if you have any kind of questions, you can always reach out to them regarding the labs and so on. I hope everybody has already ordered the components and maybe most of you already got your components for the lab. Please go over this PDF to know what are your in-lab sections and pre-lab sections. Again, keep in mind that your pre-lab section, that has 80% of the grade. So for example, these are all the pre-lab assignment that you need to do before you go to the first lab. So make sure that you have a good understanding about Thevenin and Norton sources, which you should have from your 3111. And there are a few questions that are asked here that you need to calculate, let's say, the output voltage for both circuits and so on, the Thevenin and Norton equivalent resistances as well. And make sure that you complete all of that before you go for the lab on the first day. Right? So that pre-lab section is 80% of the lab grades, and in-lab section is only 20%. And also to help you with the labs, I have also attached a video over here, this last link in lab 1. So that's basically how do you solve the problems, or basically the pre-lab section that is given in for your lab 1. So one of the TAs in the earlier years, so he recorded this video. So please go through it. That will help you understand the lab problem, the problems that are given in your lab assignment. And it will also help you understand some of the concepts better. Okay, so please go through this video before you actually start working on your lab 1. Any questions? All right. So all right. So we were discussing feedback in the previous circuit, previous class, and we'll take a look at a few more examples, and then we'll delve into the details of op-amps and feedback-based circuits for op-amps. Now, one important thing that I'd like to emphasize in today's class, and I'd like you to remember this and it will be important for any circuit course that you take in future. So positive and negative feedback, we already understood what are the differences or what are these two concepts that, and we looked at an example that when your body temperature is rising, let's say in this Florida heat, you might sweat, and the purpose of sweat is to reduce your body temperature, right? So that's the negative feedback, that if the temperature rises, if body temperature exceeds 37 degrees centigrade, then there would be some physiological triggers that will happen. And because of that, the temperature regulatory center in the brain that will ask your sweat glands to emit little bit amount of sweat depending on what your body temperature is, so that your body temperature comes back to 37 degrees. So that's called a negative feedback, because if the temperature increases, you try to reduce it. So you'll provide it a negative effect to whatever has been happening. And that's why it's called a negative feedback. On the other hand, if you had provided a positive feedback, the reverse would have happened, that the body temperature will keep on increasing more and more until it cannot increase anymore, right? So you don't want those kind of conditions. That's why negative feedback is something that we'll see in most of the physical systems. Okay. Now, coming back to why I repeated all of this, that what was required of the negative feedback system, that your body temperature was 37 degree. Somehow your body knows that it is supposed to be at 37 degrees centigrade. So whatever happens in the external environment, your body will try to have some kind of a feedback so that the body temperature goes back to 37 degrees. And the difference between the actual and the expected temperature becomes 0. Right? The expected temperature is 37. The body will do something, some sort of negative feedback system, so that the actual temperature is also 37. What is the difference between the two? 0. Now, if you think 37 degrees is your reference point, in electrical circuit terms, if that is your ground, if that is your reference point, the difference from the reference point becomes 0. And that is the concept of virtual grounds. Right? So you may have heard about virtual grounds in 3111. Virtual ground means that voltage of a particular point or a particular terminal in your circuit is same as the reference terminal. Now that reference could be an absolute reference such as DC 0, or as you'll see in the examples that they are basically referring to AC grounds, that any DC voltage could be an AC ground, right? The goal of your system would be to have a zero difference with respect to that reference point. And that zero difference can only exist if you have a negative feedback system. When you have the system in open loop, let's say your body does not have this feedback system, you'll never be able to stabilize the body temperature at 37. So an open loop system does not have the virtual ground property. Similarly, a positive feedback system does not have the virtual ground property. The virtual ground property is applicable only if you have a negative feedback system. Okay, so keep that in mind when you're solving the problems or whenever you see a circuit from this point onwards. It may be in this course, it may be in any following circuit course that you take. The virtual ground property is only applicable if you have a negative feedback. It's not an universal truth that there would always be a virtual ground. All right. So in the last lecture, we looked at the voltage series feedback. We looked at the derivation of the closed loop gain. And we found out that the closed loop gain reduces as compared to the open loop gain. So in this particular equation, let's see if I can use the pen. So A is your open loop gain. And open loop gain was for this feed forward system, the original system that was working in the feed forward open loop condition. And the gain for that system was A. That is in your numerator. In your denominator, you have this 1 plus A beta, where beta is the feedback gain. So your open loop gain, which was A, now reduces to A divided by 1 plus A beta. Right? And we also discussed in the last lecture that it's easier to stabilize the beta network because it's usually a ratio of resistances or ratio of capacitances. We'll see examples. You have already seen some of those examples in your 3111, which I would like to relate with this concept. Now, beta network is usually a resistive network, which means that the ratio of resistors generally stays constant across PVT. If you create those resistances or buy those resistors from the same batch, which have been manufactured by, let's say, one of the resistor manufacturers, even if, let's say, 1 kilo ohm becomes 1.1 kilo ohm, and maybe 1 mega ohm becomes 1.1 mega ohm, generally they go in the same direction if they're manufactured in the same batch. So the ratio of those two resistors will remain the constant that you'd like to have. So 1 mega ohm versus 1 kilo ohm is same as 1.1 mega ohm divided by 1.1 kilo ohms. So that is the reason why stabilizing the beta network is usually easier. On the other hand, stabilizing the gain A is not very trivial. So you have all of you bought these op amps for your labs, and you might see in the open loop condition, everyone's gain of that op amp will be very different. Right? Someone like, and it may not be only 5 or 10%, it could be 20, 30% in certain scenarios. However, if you write this down as, let's say you divide your numerator and denominator both with A, it becomes 1 divided by 1 over A plus beta. Now, if your A is very high, 1 over A is kind of, you can approximate that to be almost 0 if A is very high. So this entire equation just becomes 1 over beta. And if your beta factor is less than 1, 1 over beta will be more than 1. You'll still have a gain. However, because beta is a stable value, your 1 over beta becomes a stable value for the gain. That's how the stabilization comes in when you're using these negative feedback systems. Yeah. But one important thing is that your gain is reducing. Your gain is reducing by a factor of 1 plus A beta. If you look at the bandwidth of the entire system, again, some of you might have seen this chart in your 3111, the op-amp's gain versus frequency looks something like this, what you see on the left-hand side. So at very low frequency near DC or 0 hertz to a certain frequency, you generally have a fixed amount of gain. And then that gain starts falling because, of course, you cannot make your op-amp work at infinitely high speeds. Right? So there would be a limit in terms of the speed that your op-amp can achieve. And that is generally dependent on the bandwidth of the op-amp. That, okay, after a certain frequency, the gain of the op-amp itself drops. Now, this curve is for something that is called a first-order op-amp, or basically a first-order amplifier. which means that after a certain point, if you increase your frequency by 10 times, your gain will reduce by 10 times. So there will be a one-to-one relation, and that's called a first-order amplifier, that you increase your frequency by 10 times, you reduce your gain by 10 times. What does that mean? That if your bandwidth, that is the point where your gain starts falling, and you can also define your bandwidth as the half-power bandwidth, that means that, and we discussed in the last class regarding this, that what does half-power means? It means that your power at the DC level or at lower frequencies is, let's say, a square. Maybe again, let me write that down. So let's say the amplitude of gain, or basically the voltage gain, is A at this point, which means that the power gain is A square. And at half power point, your power gain would be A square divided by 2. That's why it's called half power. And if power is A square over 2, the voltage gain is square root of A square over 2, which basically becomes A divided by square root of 2, or A divided by 1.414, or that is equal to 0.707 of A. We saw that table in the last class. All right. Now, what is meant here is that the full power bandwidth, or basically the bandwidth of the system, is, let's say, something, let's say F, or F of op amp, or let's call it F for the time being. Now, what is important here is that the gain of the op amp is reducing in this direction. And if it is a first order op amp, as you increase your frequency by 10 times, the gain will reduce by 10 times. What does that mean? That at this point, the gain bandwidth product, at the point where you have the bandwidth, the gain bandwidth product, if your gain is equal to A, so let me just remove the A squared terms because they were representing power. But if your voltage gain is equal to A, and then if your bandwidth is F, then gain bandwidth product is just called A times F. So A times F is your gain bandwidth product. You can also call it, let's say, F bandwidth. So in some books, you'll see that it is called F bandwidth. Now that gain bandwidth product is basically the multiplication of your gain and your bandwidth. What is interesting is that because for the first order op amp, as you increase your frequency by 10 times, your gain reduces by 10 times. The A times F bandwidth product remains constant on the right-hand side of this bandwidth curve, right? Because as your frequency becomes 10 times more, your gain becomes 10 times less. So the multiplication of those two always remains constant. And that's why it is generally said that for a first order op amp, the gain bandwidth product remains constant. You might have heard about this, again, in 3111 or in your labs, but and also in the data sheet of op amps, you'll see the gain bandwidth product. What does that mean? That your gain times bandwidth, which is this A times FBW, will remain constant on the right-hand side of the gain, the bandwidth as well. So for example, at this point, your gain is this much. Your gain is only this much, but your bandwidth is here, right? Because your x-axis is frequency and your y-axis is your gain. So at this point, your gain bandwidth product, the area of this rectangle will be same as the area of this rectangle over here. The gain bandwidth product will be exactly the same. Because as your frequency increasing by 10 times, your gain is reducing by 10 times for this first order op amp. Now, what would that mean is that there would be a frequency where your gain will be equal to 1, right? On the right-hand side, there would be a frequency when your gain will be equal to 1, and that is called your unity gain frequency. Because if you just extend this curve toward the right-hand side, there would be a crossover point with the x-axis here, where this x-axis represents a gain of 1, which is equal to 0 dB. So that's the value of the gain along the x-axis. Now your gain bandwidth product will still remain the same. If your gain becomes 1, your bandwidth becomes gain times bandwidth. Original gain times original bandwidth. That will be your bandwidth at the unity gain point. And that's usually called an unity gain frequency or a transition frequency. Now, all of this is true for a first order op amp. If the op amp is second order, third order, we'll discuss that later in the course. This will not be true. This is only true for a first order op amp where After the bandwidth, if you increase the bandwidth by 10 times, your gain reduces by 10 times. Okay. But why did we say all of this? It's just to establish that your open loop gain multiplied with open loop bandwidth will be same as your closed loop gain multiplied with closed loop bandwidth. Now, in the last slide, in the previous slide, you already saw that your closed loop gain reduces when you have a negative feedback. Your open loop gain was A, your closed loop gain was A divided by 1 plus A beta, right? That's what we saw in the previous slide. Let me go back. So your open loop gain was A, but your closed loop gain, after having the feedback, is a reduced version of that open loop gain. So if your gain reduces, your bandwidth will increase. So that's another effect of your negative feedback, that your bandwidth can increase by applying a negative feedback to the system. And that is very useful in a practical system. So for example, some of you, let's say you may buy an audio amplifier, and let's say that audio amplifier has a bandwidth, a 3 dB bandwidth or a half power bandwidth of maybe only about 20 kilohertz. Right? Now, can you use the same audio amplifier to amplify signals which are at a larger frequency, let's say 1 megahertz or so? You can, as long as the gain bandwidth product is more than 1 megahertz. So you can always apply a feedback system so that your gain reduces and your bandwidth increases. Because your gain bandwidth product is remaining constant, you may end up with a lower amount of gain, but you can support that higher bandwidth. So it's always possible to do that if you're building such a system. Questions?
Yes, maybe a simple question. But so you said unity gain is when it ranges 0 decibels, but half hour isn't half hour when it's negative 3 decibels?
That's a good question. So negative 3 decibels. So the half power does not mean the gain is negative 3 decibels. It means it's 3 decibels lower than the original gain. Right? So at DC or at low frequency, you have maybe you have a gain of 40 dB. Right? Half power means 37 dB gain. So 3 dB lower than the original. Okay. Question? Yes. So it's up to a frequency. What does bandwidth mean? Bandwidth means that up to a certain frequency, your circuit works as expected. Right? So your op-amp will not work for infinite frequency. Let's say you have terahertz frequencies and you buy a 50-cent op-amp from the market. That will not work at terahertz frequencies. Like probably it will just work at kilohertz frequencies. Right? Bandwidth means at what frequency does it work? And this is the curve. Like if you look into any op-amp data sheet, you'll see a curve like that, which will tell you that up to what frequency you can expect this flat gain. So, oops. So your gain will be flat. So your gain will be flat up to a certain frequency, and after that it will start dropping. And the point till which your gain is flat, that will be called the bandwidth. After that point, your gain will start dropping. But your gain bandwidth product for the first order op-amp will be a constant, which means as you go to the right-hand side of this original open loop bandwidth, by applying, let's say, closed loop feedback. So your gain will reduce, but your bandwidth will increase in that case. All right. So one last thing that we'll take a look at on the matter of feedback system is impedances. That as you apply a feedback, depending on whether you are applying voltage series, voltage shunt, current series, or current shunt. So there are 4 types of feedback that is possible. So of course, if you go back to this original table or these diagrams, voltage series means your output is voltage, and series means your input or feedback quantity is also voltage. Voltage shunt means your output is voltage, but your feedback quantity and input quantity are current. Current series means your output is current, your input is voltage. And current shunt means both your output and input are currents. So there are 4 types of feedback possible. And depending on those 4 types of feedback, your output and input impedances will also change. Now, what is meant by output and input impedances? That is the Thevenin equivalent output impedance or the Thevenin equivalent input impedance to your black box, which is the circuit. So let's just take a look at one example for voltage series feedback, that what happens for the input impedance with feedback. So ZIF, so that is Z stands for impedance, I that is standing for input, and F is with feedback. So your ZIF is basically your VS, that is the voltage that you provided at the input, the original voltage source that you provided at the input, divided by the current II, that is the input current that you see for the entire system with the feedback in place. Okay. So II, so that is the current that is, now you can break down the Vs and II, these quantities. So your current II, that is going to be V in divided by Z in. So whatever current that so let's say this Vi is the input to your amplifier in the open loop scenario. So first, let's just forget about the feedback for a moment. Let me see if I can use the pen. For some reason, it is not coming up. So I'll just use my pointer as a pen, maybe. Let's see. Okay. So let's first assume that the feedback network is not present at all, right? That's how you know that what would happen in the open loop scenario when you don't have the feedback. So let's say the lower portion, which is over here, is not present at all. Let's just assume that for a moment. So your amplifier has an input voltage of Vi, and amplifier has an input resistance of Zi, input impedance of Zi, which means that the amplifier will have an input current of II, which is Vi over Zi, just from Ohm's law. Now, what is Vi? What is the input voltage of the op-amp? You know that if this is a negative feedback system, that's going to be Vs minus Vf. So whatever input voltage that you started with, minus whatever voltage you're feeding back. So Vs minus Vf is your Vi. Now, what is Vf? Again, these are just the same nomenclatures and same equations that we used last lecture as well. So Vf is the feedback voltage, which is beta times Vo. So you're feeding back a part of the output voltage, which was Vo, back into the input side, and Vf is just beta times Vo. So you just write that down, Vs equal to beta times Vo, and your Vo, how much is Vo? Vo is A times Vi. So Vo is the output voltage at your op-amp or at the amplifier over here. So output voltage is gain times the input voltage of the amplifier. So Vo you can write as A times Vi. Okay. So now you have this equation, II is equal to Vs minus beta times A times Vi divided by Zi. So I times Zi is equal to Vs minus beta times A times Vi. So from here,
I think the Zoom stream stopped working.
The Zoom screen stopped working. Okay, all right. Yeah, I think that happened. Let me see. Okay, I may have to reshare the screen on Zoom. Let me do that once again. All right, now you should be able to see on Zoom as well. Okay, so it's basically the same mathematical operations that we had used in the last lecture as well. So you're trying to find out your input current as a function of your input voltage and the original input voltage Vs and the voltage that your amplifier sees at its input, which is Vi. So you just did the same mathematical manipulation as we did in the last lecture, and you end up with this equation that your I times Zi is equal to Vs minus beta times A times Vi. So your Vs, you can write that as I times Zi plus beta times A times Vi, and you can write your Vi as II times Zi. So again, just applying Ohm's law, KCL and KVL at different points. So it's not nothing fancy. And from here, you can find out the ratio of Vs over II, and you'll see that Vs over II becomes Zi times 1 plus beta A or 1 plus A beta. What does that mean? That originally your input impedance was Zi for the amplifier. Just for the amplifier, your input impedance was Zi. However, when you use this voltage series feedback, your overall input impedance increased. So Vs over Ii, that if you look at again, for some reason, I'm not getting access to the pen anymore. But let's see. Yeah. So if you look at the input from here, the input impedance from here, that would be different from the input impedance that you look here, right? Because in between you are having this feedback. So of course, the input impedance that you see from the source will be different from the input impedance that you had for the original amplifier. For the original amplifier, your input impedance was Zi, which is this term. But for the entire system, the input impedance that you see, that is Zi with feedback, is going to be Zi times 1 plus A beta. So your input impedance actually increased in the meantime when you applied the feedback. And similarly, you can calculate your output impedance as well. And similarly, you can do it for all 4 different types of feedback systems, which we have done here, that for voltage series, current series, voltage shunt, and current shunt. What happens to your ZIF, that is the input impedance with feedback, and output impedance with feedback. So we just proved in the previous slide that your input impedance with feedback is going to be increased. Similarly, you can show that your output impedance with feedback is going to be decreased for voltage series. Now, if you have a current series feedback, these can be different. If you have a voltage shunt feedback, again, both of them is decreased in this case. And for the current shunt, the input impedance is reducing, but the output impedance is increasing. So you see that there are like so many different, depending on your choice of feedback and depending on whether you're looking at your input and output, your impedances can increase or decrease. And all of these can become very confusing. But I'll tell you maybe a shortcut method to remember, or maybe very easily conclude that whether your input or output impedances are increasing or decreasing. So think about your voltage series feedback. What does happen in a voltage series feedback? You have let's say, an original amplifier network. You have a beta network, which is your feedback network. You subtract your original incoming voltage from the, you subtract your feedback voltage from the original incoming voltage, and then there you have. So your input is over here, and your output is over here. So what you're doing with voltage series feedback is you're taking some amount of voltage from the output. It is called voltage series. That means your output is a voltage, right? You're taking some amount of output voltage, feeding it back at the input. That's what you're doing. Think about Ohm's law. Ohm's law says impedance is voltage over current. If you're taking away some amount of voltage from the output, your voltage over current is reducing at the output, right? You're taking away some amount of voltage from the output. Although that is not what actually happens, and you should be doing those KCL, KVL based calculations that we just did in the previous slide. This is a way to remember it, that for a voltage series feedback, you're taking away some amount of voltage from the output, feeding it back to the input. So you're reducing you can think of it in this way, that you're kind of reducing the voltage at the output, increasing at the input. Because you're taking some voltage from the output, feeding it back, right? So according to Ohm's law, voltage over current, that's your impedance. So you're taking away voltage from the output, so your impedance will be decreased. And you're putting voltage back at the input side, your impedance is increasing because now you have more voltage at the input side, assuming that the currents are all same, right? So this is a quick way to remember. Now let's apply the same philosophy for current series. Current series means your output is current, your input is voltage, correct? So you're taking some current away from the output, feeding it back in voltage form at the input. So you take away some current at the output. You're reducing the current at the output. And imagine that your voltage is staying same. So what would happen to your impedance according to Ohm's law? Your current is reduced. If voltage stays same, your output impedance is increasing. How much is it increasing? By the same factor 1 plus A beta. How much will it reduce? By the same factor 1 plus A beta. The factor is always the same. That is 1 plus A beta. So at the output, your output impedance is increasing by the same factor 1 plus A beta. At the input side, what is happening? You're feeding back some amount of voltage. So current series means your input is voltage. The second term is called series. And you can only have voltage sources in series. You cannot have current sources in series because they will fight. So if your input is voltage, you're feeding back some amount of voltage, again, according to Ohm's law, your voltage is increasing, current stays the same. That means your input impedance is increased, right? How much does it increase? By the same factor 1 plus A beta. Take another example, current shunt. Your output is current, input is current. If your output is current, you're taking away some amount of current from the output. Think about Ohm's law once again. If your current is reducing, your impedance is increasing. And you're feeding back some amount of current at the input. So your current is increasing. That means your impedance is decreasing. Right? This is a very quick way to remember what happens in each of these scenarios. There are 8 different scenarios, but you can remember all 8 scenarios directly if you just remember this. That again, take an example of voltage shunt. Your output is voltage. So you take away some amount of voltage from the output. If you reduce your voltage, your impedance will be reducing. And shunt means your input is a current. So you're feeding back some extra amount of current. If your current is more with the same voltage, your impedance is decreasing. Right? Just by remembering Ohm's law and what is the definition of voltage series, voltage shunt, and current shunt, you can remember this entire table. Any questions? Yeah.
That's like series just means both the input is a voltage.
Series means input is a voltage because you can only connect voltage sources in series. You cannot connect current sources in series. Shunt means it's current. Okay. And I mean, this is again a nomenclature which is followed by everyone in the world, that the first term will be what you have at the output. The second term is what you have at the input. Right? For definition of feedback. And that's all there is when you talk about feedback. Right? The feedback could be voltage or current. You think about how you can increase or decrease impedances, and that's about it. Yes. That's a good question. So when you talk about a type of amplifier, so for example, voltage amplifier or current amplifier, right? So current amplifier means your input is a current. And of course, as we're talking about amplifiers, we're always talking about AC amplifiers, right? So you'll have an oscillating sine wave maybe at the input. And if you think that or if your input quantity is current, then it's, yes, that your current looks like a sine wave, which may mean your voltage also looks like a sine wave if your impedance is linear, right? If your impedance is constant, then your current and voltages look the same. But if your impedance is changing for some reason, and those conditions can happen, we'll probably not look at that in this class, but those are more complex real-life scenarios. When your impedance itself changes as you're changing the current, then your voltage may not look like a sine wave anymore, even if your current looks like a sine wave. All right. So that's all I had to talk about for feedback. Now let's go into a little bit details in terms of op-amps. And this will just be a very brief summary of what you learned in 3111. So I'll go through op-amps a little faster. But let me know if you have any kind of questions. So there are 2 terminals in an op-amp, inverting terminal, non-inverting terminal, and there is 1 output. So all of you know this already, right? So two input terminals, 1 output terminal. Of course, you will also have power connections. So explicit ground and explicit VDD. Generally, those terminals are not shown in the book, but of course, a real op-amp will have those. What are the ideal op-amp properties? Infinite voltage gain. In reality, it will not be infinite. Ideal op-amp has infinite input impedance, which means no current flow into the input. But in reality, there could be a large input impedance, but not infinite. Zero output impedance and infinitely fast, which means that the ideal op-amp has infinite bandwidth as well. But in truth, op-amps are limited to maybe a few megahertz. Many op-amps are also in the range of kilohertz. Now, without the feedback, if you have an open loop system with an op-amp, so you just have 2 inputs and you have output. There's no feedback, nothing. So the formula for this op-amp is output voltage is equal to gain times V plus minus V minus. So whatever voltage you have at the positive terminal, minus whatever voltage you have the negative terminal, multiply that with gain, that will become your output voltage. So if your V plus is more than V minus, the output goes positive. And if your V minus is greater than V plus, the output goes negative. Now, you know that the op-amp has ideally infinite gain. Even practically, it can have very high gain, like, for example, it is mentioned here, 200,000. Right? So that kind of gain is also possible in an open loop scenario. But that makes the system practically useless. Because any very small amount of, so let's say you have a millivolt at the input, or millivolt difference between V plus and V minus at the input. That's a very small difference between the two. That millivolt will be multiplied by 200,000. So your output will be 200 volts if we assume that it will still stay linear. It will not, but if we assume that 200,000 gain is feasible, then your output will be 200 volts. What do you do with such a big output voltage, right? And probably it's useless, first thing. The second thing is that, of course, there will be VDD and ground in the system, and your VDD could be 5 volt, your VSS could be minus 5 volt. So your signals will be clipped. Instead of 200 volts, all you'll be seeing is 5 volt clipped signals, square waves. And that's why generally you use the op-amp in a negative feedback loop to have a better, so of course, more stable gain, as you have seen in the feedback slides. Also, at the same time, it becomes more useful. Let's say you amplify the 1 millivolt signal to 100 millivolt. So you just need a gain of 100 for that. So you can apply a closed loop feedback for the open loop op-amp and get that kind of gain. Okay. Now, you can have positive feedback or negative feedback, as we had discussed earlier. Negative feedback means you'll take the output, feed it back at the negative terminal of the input. That's what it will essentially boil down to. For positive feedback, you'll take the output, feed it back at the positive terminal of the op-amp. And we're saying that positive feedback is bad. That is bad in terms of amplification, because eventually with positive feedback, you might run into oscillations, which you may not want for an amplifier. So you either want to build an amplifier or an oscillator. And many times what students do in the class, and I have done that too when I was a student, that I wanted to build an amplifier, it became an oscillator. Next time I wanted to build an oscillator, it became an amplifier. So there's a very fine balance between the two, and make sure that you understand the positive and negative feedbacks that are happening in the system. In lower frequencies, it's easier to control them. When you go to higher frequencies, hundreds of megahertz or gigahertz range, it becomes more and more difficult. And that's why there are graduate level classes in RF electronics, where you get to learn how to control your amplifiers versus oscillators at high frequencies. Okay. Some of the golden rules on op-amp. Again, these are all repetitions of your 3111. So that's why I'm going a little faster. That the input of the op-amp will draw no source current. So the inputs of the op-amp will not draw any current, because we'll assume that the input impedance is infinite. The output of the op-amp can do whatever it can. What does whatever it can mean? That if you have basically, if you assume that your output of the op-amp has zero output impedance, then it can drive any load that you connect at the output. Right? If you have a voltage source, so the op-amp, you know that the op-amp can be represented as a voltage controlled voltage source, right? So let me get my pen once again. So your op-amp, the very simple model of your op-amp, which was your homework 1, problem number 4, is basically let's say a voltage controlled voltage source. And this voltage controlled voltage source, if it has zero output impedance, let's say this output impedance Rout or RO is equal to 0. And then you connect it to some kind of a load at the output side. Now, if your RO is equal to 0, then all the voltage drop will happen across this output resistance RL, right? There would be no voltage division between the two. I mean, there would be a voltage division, but that voltage division is RL divided by RL plus RO. And if RO is equal to 0, which is the case for an ideal op-amp, if RO is equal to 0, that voltage division ratio will be equal to 1. Right? So ideally, you want your output impedance of the op-amp to be very small, ideally equal to 0. It may not be possible to create an op-amp with an RO equal to 0. But the meaning of this sentence is that if your RO is very close to 0, you can drive anything, any resistance that you have. You can have a 1 milliohm resistance. That's a very, very small amount of resistance, which means that the current flow will be very large. And what does load actually mean? Load means current, right? So if your resistance is very, very, very small, let's say you have a 1 micro ohm load, that means the current flow will be very, very large through that 1 micro ohm load. Even though even 1 micro ohm is probably not possible in real life, but if you assume that 1 micro ohm is possible, then the current flow will be very large, which means the load is very large for a 1 micro ohm load. But if your RO is equal to 0, you'll still have all the voltage across that 1 micro ohm load resistance. So your output of the op-amp can do whatever it can. Even for a 1 micro ohm load resistance, it can still drive it. And by driving, what we mean is that you'll have enough amount of voltage or the full voltage across that load resistance. However, in real life, your RO will be finite. It will not be 0. That means if you have a 1 micro ohm load resistance, again, if it is possible to have a 1 micro ohm load resistance, then most likely all the voltage drop will happen across RO and none of the voltage will be across RL. So a real op-amp cannot drive a 1 micro ohm load resistance. A real op-amp cannot possibly drive a 1 ohm load resistance as well, right? It will be very hard. But if it is, let's say, tens of ohms, hundreds of ohms, kilo ohms, mega ohms, it's generally easier for the op-amp to drive it. Okay, inverting amplified example. We have solved one of them in the class on the board, I believe, in a few lectures back. Also, you have learned this in your 3111, that if you just apply the golden rules, that the negative terminal is at virtual ground. Why do you say that your negative terminal is at virtual ground in this case? Because you have this positive terminal which is at, let's say, AC ground. It could have a DC voltage, but in this case, you're only interested in op-amp based amplification, which means your input is AC, your output is AC, and then you can have an AC ground over here. And the other node is a virtual ground, because again, you have a negative feedback here. And with that negative feedback, you'd like to stabilize the voltages at different points or different terminals in this op-amp circuit. So if this point is ground, this point is also a virtual ground. Right? The example that we discussed in the beginning of the lecture. And current through this resistance R1, that will be V in over R1, because if this point is V in, this point is virtually 0, then the current will be V in over R1. All of that current will go through R2, because no current can go inside the op-amp. All of that current will go through R2, which means that the voltage drop across R2 is going to be IF times R2, that same current times R2, and you already know IF is equal to V in over R1. So you can write down IF times R2 is V in times R2 over R1. So output voltage V out, because the current is flowing in this direction, output voltage V out will be less than 0, because this point's voltage is 0, it's at virtual ground. So output will be 0 minus V in times R2 over R1. So minus V in times R2 over R1. That means that your gain is minus R2 over R1. Again, what does negative gain actually mean? Many of you already have written down in your homework problem that if your input looks like a sine wave with positive half cycle first and negative half cycle after that, your output will look like negative half cycle first and positive half cycle later, right? So that you'll have a 180-degree phase shift, and that's what is meant by this minus sign for the gain. So, and also that is the reason why it's called an inverting amplifier. You're amplifying it, but at the same time inverting the input voltage. Right? You're inverting the input voltage and amplifying it. Okay, so that's your inverting amplifier example. Similarly, you can solve the non-inverting amplifier. I'm not going to talk about that in detail because again, it was in your 3111. For your non-inverting amplifier, the gain is 1 plus R2 over R1. You have a positive gain, 1 plus R2 over R1. And what does positive gain means? That if your input is this sine wave, output will probably look like this. There will be no phase shift between your input and output. You can have a summing amplifier, summation of voltages. Again, you can have V1 voltage with R1 resistance, V2 voltage with R2 resistance, And using KCL, you can add these two currents over here at these terminals and solve the system using the same method that we had done for the first scenario, for example. And in this case, you'll get output voltage, which is equal to minus RF times V1 over R1 plus V2 over R2. If R1 is equal to R2, you get a sum which is proportional to V1 plus V2. You can also have a difference amplifier. Again, this is the circuit for your difference amplifier, and your output voltage will look like R2 over R1 times V plus minus V minus, where V plus is the voltage that you're eventually applying or connecting to the plus terminal, and V minus is the voltage that you're connecting over here. And output voltage will be proportional to the difference of those two voltages in this case. You can also have a differentiator or a high-pass filter. If you connect a capacitor in the series path on the directly connected to your Vin, and in the feedback path, if you connect a resistor, then you can again write down those equations that for a capacitor Q equal to CV, the charge stored across the capacitor is C times V. The current through the capacitor is dq dt. That's basically the derivative of the charge with respect to time. And dq dt will be C dV times dt, because Q is equal to C times V. If the capacitor value does not change with time, however, your voltage is changing with time, so you have C dV dt as your current through that capacitor. And then again, that amount of current, the entire current flows through the resistor. So the voltage drop across resistor is RC times dV dt, and the output voltage is going to be minus RC times dV dt. Right? So you have a derivative of the voltage at your output, derivative of the input voltage at the output. So this acts as a differentiator or a derivative function, which also acts as a high-pass filter. Why does it act as a high-pass filter? Because let's just think about a square wave for the time being. And what does the frequency response of a square wave looks like? The frequency response of a square wave will have multiple components. It can have a fundamental component, and it can have many high frequency components. So if this is time and this is amplitude, if you do an FFT of the square wave, and again, some of you who have who already know about Laplace transforms or have taken a signals and systems class, you know that for a square wave, the transfer function or the FFT looks like this, that you have your amplitude on the y-axis, you have frequency on the x-axis, you'll have a fundamental frequency at the frequency of the square wave, then you will have 3 times the fundamental. So if this is f0, you have 3 times f0, there would be a component. There would be a component at 5 times f0, 7 times f0, and so on. Now, if you have a differentiator, that means you're taking a derivative of the square wave. You know that for the derivative, you will only have an output when the square wave is changing. It is changing from 0 to 1 or 1 to 0. When it is flat, when it is constant, the derivative of a constant is 0. So you'll only have these two edges, and the derivative of the square wave would look something like this. That at the positive edge, you'll have a positive spike, and at the negative edge, you'll have a negative spike. And if you look at the transfer, the FFT of this particular waveform, you'll see that the first term is not present, but the other terms are present. The higher order terms are present. So your high-pass filter or differentiator also acts as a high-pass filter. It gets rid of the fundamental component or low-frequency components. Similarly, an integrator will work as a low-pass filter. So that's in the next slide. Your integrator, you can build an integrator if you have a resistor here and a capacitor in the feedback path. And again, if you write down the equation, you'll see that your output is minus 1 upon RC times integration of V in dt. And it's by using the same equations that we did in the last slide. It's just that the location of R and C are flipped, and that makes it an integrator from a differentiator. And integrator also acts as a low-pass filter, just like differentiator acts as a high-pass filter. Again, most of these things you have learned in year 3111. This is what an ideal op-amp looks like, an ideal op-amp behaves like. But the goal of our next few lectures would be to look at non-ideal op-amps. And we'll start with non-ideal op-amps on Wednesday's lecture. Okay. So let's end here. There are some more optional reading, you may go through it. But Overall, in the next lecture, we'll start with the non-ideal op-amps and look into the different behavior of these op-amp based systems.